Now I want to move on to a different type of carbon-carbon bond formation. It's taking an aldehyde and making alcohol, and it's doing it using an enolate. First, you take your ketone, that's your starting material, and then you want to make the enolate, and you want to make lots of the enolate because you want to do an Aldol reaction. So you add LDA, a very strong, bulky base. Then when you've generated the enolate, and not before, so you've used up the LDA, then you add the aldehyde. Now aldehydes are more reactive than ketones as electrophiles, so this then picks up the enolate and produces the new carbon-carbon bond. That is an equilibrium process. The anion that's produced at that stage, this localized alkoxide anion, is less stable than the enolate that's produced it. It's accessible, but you're climbing up an energy hill in that step. That anion can be protonated by a water molecule, and that produces the alcohol, and that alcohol then has an alkoxide as the charge carrier. But when you compare LDA, the starting point for this reaction, with alkoxide, then overall there is a drive that accounts for the Aldol reaction. Here's a different concept. This Aldol reaction is not a mixed Aldol reaction. This enolate is generated from the same molecule, which is here in this example serving as the electrophile. Which type of base do we choose? If we add a powerful base, we're going to push this equilibrium right over to the enolate form. But we need some of the material to be in the keto form because that's the electrophile. We need to change strategy from what you saw just now for the mixed Aldol reaction to this alternative example where the ketone is serving both as the source of the nucleophile and the electrophile. What you need now is an equilibrium at the top of this slide where you have a good concentration of enolate and a good concentration of the keto form. We need them both present together in solution to be able to react together. So the right choice of base now is the hydroxide ion. So we have at any one time some nucleophile, some electrophile. Now the Aldol reaction can happen, making a new carbon-carbon bond between the nucleophilic center of the enolate and the electrophilic center of the ketone, and to complete that process, transferring the electron density onto the oxygen atom. So this alkoxide anion, that's the first intermediate, can pick up a proton from the water molecule, and that will produce the Aldol product here with the alcohol and the original nucleophile now back as the ketone. So that's one of the typical Aldol products. If you do this with a high concentration of base, then further chemistry can happen after that stage. So let's see the potential now for that further chemistry. So far, we've been climbing uphill somewhat. We get an equilibrium here, but once we make the carbon-carbon bond, we're at localized anion. When that deprotonates a water molecule, we're still at localized anion. But that localized anion is the same anion we started with. It's the hydroxide ion. So we're back where we started. We can deprotonate that ketone a second time to generate a new enolate, and that new enolate is different from the first one in a key respect. It's the enolate that's generated from the Aldol product. That means it has the carbon-oxygen bond that came in through the functional group in the electrophile. That carbon-oxygen bond is a leaving group, and the leaving group is next to the reactive 3-atom pi system of the enolate. So we can break that carbon-oxygen bond, and in that process extend the pi system, and the other product of the Aldol chemistry is an alpha-beta unsaturated ketone.